So leading up into this, we talked about probability as a whole, we talked about conditional probability, where probabilities come from, and we also looked yesterday at two discrete distributions, which were the Poisson distribution and the binomial distribution, both of which are used to describe phenomena that have actual whole numbers, like the number of people who arrive in time for a lecture, or the number of male babies you have, or the number of flights that crash on the way to America, things like this. Okay, so we have, what is the normal distribution? Now, to start off with, like I said already, it's the cornerstone of modern statistical theory. And this is what we have to remember, is that all of the stuff we work with in statistics is a theory. It's a way of making sense of the world. And the world usually, and especially physical phenomena, usually follows certain rules, but sometimes it doesn't. It was first identified, or by either, depending on which book you read or which Wikipedia or whatever, some people say it was this guy Quetelet and Galton, or it was Carl Gauss. But it was around the same time, around 1870. And what happened was they especially in physical experiments, they found that the errors in measurement followed a certain pattern. Like, say you're measuring the length of something, and you take lots of different measurements. Sometimes you'll be a little bit off, plus or minus. Sometimes you'll be right on, whatever that is, and sometimes, occasionally, you'll be quite a long way off. But mostly, you get near the middle. And this is what they found, and this is where this bell curve comes from. And it appears in lots and lots of different, the same pattern occurs over and over, especially in nature. So things like people's heights, people's weights, generally follow that. The people's ages, and then we come to plants or animals, especially sheep weights, length of wool, things to do with agriculture, and then in industry as well. When we're trying to produce things of a certain length, there'll be variation, and mostly there'll be variation, small ones either side. Occasionally you get a bigger variation on either side. And the same with weather too, if you think of it in terms of weather. Mostly you get about the same with a little bit of variation either way, but occasionally you'll get a much colder day or a much hotter day. So this same sort of idea just happens in reality a lot. It's symmetrical. Now, reality isn't necessarily symmetrical, and some of the things I've mentioned before aren't really symmetrical, and I'll explain that in a minute. What I mean by symmetrical is that you've got the same spread under the mean as you have over the mean. But even if the actual thing that we're trying to model isn't totally symmetrical, we can still use the normal distribution because it's a good approximation, and it's better than anything else we can come up with. There are other fancy distributions that people have made up to try and fit other things, but often, when you get a big sample, things go back to the normal. And in fact, the two distributions we did yesterday, the Poisson and the binomial, in both cases, if we go to large parameters or large numbers of observations, everything goes back to a normal shape. The normal distribution has two parameters. It has its mean, which is the centre, where and the mean splits the distribution in half. So half of the observations, or half of the things that can happen, will be less than the mean, and half of them will be greater than the mean. And that's what we mean by it being symmetrical as well. And it also has a standard deviation. So in fact, there isn't just one normal distribution. There is an infinite number of normal distributions with means and different means and different standard deviations. But all of them can be brought back to a single standard normal distribution, which has a mean of 0 and a standard deviation of 1. And that standard normal distribution is used a lot in statistics to compare things to, because all of the others, using these two parameters, you can bring back to the same standard normal distribution. Okay, so I've talked about how it provides a model for effects that occur in the natural world. So heights, weights, lengths, all sorts of things like that. It's a tricky formula. It's got an e and a pi in it, which I find rather bizarre, and an integral sign, none of which I really like. So we don't do the formula thing. If you want to learn about the formula for the normal distribution, you should do mathematical statistics. So that would be stage 2 in the stats department. Very few people have any idea what the formula looks like. Instead, when I was at school, we looked up normal tables. When you were doing this, probably in year 12 or 13, you may have used graphics calculators. Has anyone done normal distribution with graphics calculators? Yep, that's right. And these days, or in this course, we're just going to use Excel, because that is the thing. If you're in the business world and you want to find out something to do with the normal distribution, you will have Excel there. Now, the reason it's everywhere is because it's the sum of an infinite number of random effects. Okay, so let's have a think about a tomato. Okay, so you've got a tomato plant, and what sort of things are going to affect the weight of one single tomato on that plant? Okay, what sort of things will affect the weight of that tomato? How much water? Okay, it's not just how much water though, it's how much water it got on the first day that it was growing, and on the second day that it was growing, and how much water it got just after that particular tomato got pollinated. Okay, what else is going to affect that one tomato? Pardon? Sun, exactly. How much sun it got, whether it got lots of sun at the beginning, in the middle, or the end, and so on. Okay, so we've got almost infinite amounts of water, infinite amounts of sun. What stage it got pollinated by the bee or whatever, how many other tomatoes are sitting around it, whether it got blown on every day, and so on. So you can see, you can just come up with so many different reasons, and each one of those little reasons will have an effect on that particular tomato. So if we then collect all of the tomatoes off a plant and all of the tomatoes off a paddock full of plants, we will find that each one of them has been affected by these infinite number of different things. And that's why the normal distribution can approximate that, because it actually does a mathematical thing that combines an infinite number of random variations. And so what it does is, with this formula, it puts it all together, and what happens is you get this curve that I've been wanting to use all the time I've been talking.